Good afternoon, everyone. I am Rick Mardonato, and I will be discussing generating sets and Cayley digraph. Generators are some special elements that we can pick out which can be used to get any other elements in the group. So as an example, remember the dihedral group, the symmetries of an n-sided polygon. There are two n-symmetries in all, but we can build up any numbers of symmetries just using a small rotation and a flip. For the symmetries of equilateral triangle, we'll let P denote the rotation by 120 degrees and let F be the flip over one of the axes of the triangle. Then the six elements of the dihedral group are given by ID, P, P squared rather, F, FP, FP squared. Thus, F and P is a set of generators for the dihedral group. Let me introduce a definition. Let S sub I in such that I is in the element of capital I be a collection of sets. Here I may be any sets of indices. The intersection element of S sub I of the sets Si is the set of all the elements that are in all the sets of S sub I. That is, the intersection element of S sub I is equal to X in such that X is an element of S sub I. For all I is in the element of capital I. If I is infinite, I is equal to 1 to along the way to n, then we may also denote that the intersection element of S sub I by S1 sub 1 intersect S sub 2 along the way to intersection S sub n. With this definition, we can formulate a theorem, which is the intersection of some subgroup H sub I of a group G for I is an element of capital I is again a subgroup of G. Since we have already an idea what generating sets really mean, so let me introduce a more substantial definition that we can refer to in the future. Let G be a group and let A sub I is an element of G for I is an element of capital I. The smallest subgroup of G containing S is equal to A sub I in such that I is an element of capital I is a subgroup generated by S. If this subgroup is all of G, then S generates G and then A sub I are the generators of G. If there is a finite set of S that generates J, then J is just as finitely generated. So in a basic terms, if we have a group G and a subset of that S, we may say that S generates G and that S is the generators for G if every element of G can be expressed as a product elements of S and their inverse. Let's prove that the set 2 and 3 is a generating set of the integers under addition. We can say that this is true because we can reach an integer by adding ones and negative ones, and we can express 1 and negative 1 in terms of 2 and 3. So like negative 3 plus 2 is equal to negative 1, and 3 plus negative 2 is equal to 1. In fact, we can argue that any co-prime number is a generating of the integers under addition using this method. Once we have a generating set of graph G, we can produce a nice visualization of the group. We use directed graphs or digraphs to represent the group in terms of the generators in each generators in generating set of the finite group G. A digraph consists of a number of points or vertices that are connected by a series of arrows called by arcs. These graphs can help track the relationship between elements. The digraph shown here is the Cayley graph S sub 4 that is generated by transpositions that swap neighboring elements. And now, let's take a look at some example. And this is a very easy example of Cayley digraph. So we have cyclic group C sub 8 is equal to 0, 1, 2, 3, 4, 5, 6, and 7 with the generating set of 1. And this is a visualization of Cayley digraph. So we have vertex for every element in a group such as 0 and the arc xy for each pair xy such that x is equal to y plus 1 by the definition. So 0 here plus 1 would be 1. So the connection between 0 and 1 would be 1. So let's take a look at another example. So we have proven that 2 and 3 are the generating set under addition. So this one should look pretty familiar. This is what Cayley digraph look like. So in this case, our vertices are the integers again such as negative 1, 1, and 3. But this time, we are talking all the integers in G. In this case, we have two generators. The generators 2 connects any two integers that differ by 2. So in this case, we have, as you can see, the Cayley digraph. We have negative 1, I mean negative 3 and negative 1. The difference between them would be 2. So they are connected by the arrow that equals to 2, which is the red arrow. Well, the generators J connects any two integers that differ by 3. So between negative 2 and 1 are connected by the green arrow, which represent 3. Okay, so that is the end of my report, which is generating sets and Cayley digraph. Again, thank you everyone for listening, and once again, good afternoon.